All right, so I'd like to introduce our next speaker, Nathan Tregger of Verify. He's also the co-moderator of this session. And this is a great one to follow Ken's talk on time dependency of a slump. Nathan's going to talk about in-transit monitoring of slump or concrete rheology and what the implications are of that technology. So thank you, Nathan.
Thanks, Shiho. Thanks, Ken, for that great talk. You know, love going right after you. That's always fun. All right, so I grew up in Niantic, Connecticut. It's on the coastline. And so what I have here is from our local newspaper the day after the 1938 hurricane. So this is 20 years, just 20 years after the Abrams film. This was one of the worst hurricanes because it came essentially by surprise. They couldn't track it very well. They thought it was just going to be light rainfall, and it ended up being a huge disaster that went through. And it was something that you could actually see in our town pretty well. I mean, even the waterways were changed by this hurricane coming through. So you can see some of the pictures here. Boats, huge boats up on the dock. Of course, electricity out, houses gone, railroad tracks just destroyed. So also following Ken, you know, even in this situation, the Abrams cone could not prevent this either. So I just want to kind of make that comparison of what we've done on the hurricane side compared to what we've done on the slump side. So in 1958, you started to have weather balloons. By this time, you had people making slumps out of the slump cone. 1960s, you started to get satellites that were out there that did a good job, and we have the slump cone. 62, first Air Force plane, right? And each of these iterations, you start to get different data that was coming from it, right? Rainfall, radar, sonar, all these kind of different things. 2010, so skipping a little bit ahead, right? And in 2015, we were shooting drones into hurricanes. It was awesome. We were doing this, all right? Also in the background, you know, a couple different companies were working on looking at how to put sensors on your truck to figure out, hey, can we do something about that? And so that's what I'm going to talk about today, is some of this technology, what you get with those measurements, and what you can actually do and go ahead with those. All right, so again, evolving concrete tracking and visibility. This system here basically looks at hydraulic pressure required to rotate the drum sensor, how fast it's going. And then the big part of this with this IoT or Internet of Things is taking all of this information from each one of these trucks, shooting it up to the cloud, and finally being kind of a 21st century technology. So these systems have existed for a long time. Over 150 million cubic yards have gone through this, so that's 750 Dallas Cowboys stadiums, if you're keeping track. And what we've generated is genuinely over 1 billion data points with this information, with these systems. All right, so we're trying to say, hey, what are we doing on the weather side? And then let's see if this works. What are we doing on this? And this is just a quick animation. This is real data, so these are all the deliveries over just 2 days. And basically it's showing a certain property over time, and so you can kind of get a much better understanding of your operations, not just looking at that one delivery. All right, so what I'll talk about today is slump management at the plant, on the job site, and then seeing how we can take that to go a little bit further. All right, so what we have here is something that we do working with ready mix producers. We install sensors, and then we basically let it run and don't tell them what it's saying. All right, so we call this ghost mode. It's on there, it's recording all the data, but we don't give any feedback, so they're not making any changes. And so what we've done here is basically taken a measurement of slump as right after batch, but as long as it's mixed properly. So you batch it, mix it properly. This is the first slump reading that you'll get from that. All right. Just to show you, so this is 330,000 data points. All right, and this is across many ready mix producers. So this is not just a single one. And so what I'm showing here is basically that slump distribution compared to the target that they're going for. All right, And so now that you all learned the slump test goes from basically 0 to theoretically 12, you can see the range of this information here. It's going from -6 to 6. All right, this is real data. So this is a pretty good eye opener. You know, it's not just about you know, this being the ghost, but this is a scary thing, right? To see this kind of stuff. So what we've done is once you understand that and see that, you can start making all the adjustments. You know, figuring out what the truck drivers are doing, looking at your materials, you start to decrease this this variability. So just as an example here, this is again that plot that we just saw before. Let's see. And then in this middle graph right here, this is basically the behavior of all your truck drivers. Okay, so this is the initial slump that they get. So you can see that some drivers like to keep it an inch above target, some are 2, some are below. And that creates a problem because your batch person has to guess what they're going to do that day with that load and adjust your trim accordingly. So you have basically 2 people independent trying to do the same thing. They're all trying to help out. But with that, you're not able to get the consistency, right? Because you're kind of bullwhipping, or you think they're going to do this and they do something else. And this creates a lot of the variability that you start to see. And it's not only across different drivers, but for example, the last graph here just shows one driver over time what that initial slump is, right? It's really all over the place. So this whole thing is a team sport. It's really allowing the operation to see what's going on, maybe implement some standard procedures, maybe to be a little bit more vigilant, disciplined about it. But it's absolutely possible to reduce that. So just looking at the one side to the other and going from a standard deviation of 2 inches to standard deviation of almost 1. All right, that's a big, big improvement, especially over this. With this data. So this is another slide. So basically, you've taken care of as much as you can at the plant. What happens in transit? So one of the nice things about the system is that you're able to adjust the slump on the way. So if you're low, you get to add water, add mix up until a certain point, and then you can go from there just to try to improve that consistency. So you can track that over time, and we've learned how important that is. And I only have really one slide on this management, but I think this is one of the most important graphs that you see on the right. In the gray, this is your arrival slump versus target without managing, and in the blue is when you're managing. All right, so you can see that there's an extremely stark difference about what happens when you don't have any control mechanisms and when you do, and how you can really tighten up that standard deviation. All right, so, and the other thing that I want to point out with is the non-managed, so that's about 750,000 loads, so 750,000 data points. And the one with managed, we have over 11 million loads. All right, so this is something that obviously the ready-mix producers are adopting and using very well to get excellent control. Going again from a 2.25 standard deviation to 1.25. All right, so now you've controlled it at the plant, you controlled it at in transit, so we should be all set. It's perfect now. But really, this isn't the case. And so what I have here is basically 2 histograms overlaid on each other. So in total, this is almost 1 million data points. In this, let's see if I can do that. The blue here, right, and the dark blue is the overlap between gray and the blue. The blue here is when you've managed with the system, or the blue is when you've arrived at the site. Okay, you've done all those control factors, you got to the site, you're looking really good. And then the gray here is when they discharge. All right, again, this is over 1 million data points. So there are a ton of reasons why this happens, mostly miscommunication between ready-mix and contractors, contractors not ordering the right slump, or oversight maybe, but this isn't a one-off kind of thing. This is very persistent, and so this is another challenge that data helps you to basically address. Now that you have visibility, you can go and talk with the contractors. They can actually order the right slump, perhaps, or maybe order a different mix from the producer. But that's the conversation that gets started, because obviously all of the issues that you think about, that we start to discuss, longer set times, strength, not getting consistent product, QC, it's very difficult for QC to optimize their mixes if they don't know how it's getting poured, or they're getting data that's been obviously altered since arrive site and discharge. And so once this is brought up, there are ways to get both sides to agree, and obviously you can correct the behavior. So you can see on the right side here, it's 70,000 loads, and that arrive site and discharge are just right on top of each other. All right, so really good communication and execution by both sides. All right, so it's not just improvements that you get, let's say on the ready mix producer. Contractors see a lot of improvements here. The graph that we have here on the y-axis is basically cumulative discharged material. All right, over time. The color is the slump from target. Okay, so if you're a lot higher, a lot lower, that shows kind of the variability. This was for a curbing project. And so on your left side, you can see there's maybe an issue with the slump at around 6 hours or before 6 hours, and then it just stops. The equipment, the curbing equipment, started not working. They had to deal with that. You have a break in your production. Once the producer and the contractor are able to use the system, get real consistent, you can see the big shift on the left side to the right side. Not only doubling or almost tripling the amount of concrete you're putting down, but everything is right in order. You get, not only you have your load every time very consistently, you can start to, if this is a finishing project, your finishers would be have a really good cadence to operate with. All right, so the end game now that you see that it's possible to control at your plant in transit at the site, this is where it really starts to get interesting. This is where you can really start to optimize your mixes, optimize the amount of cement, for example. So this is just a case study for one of our contractor, actually, curbing contractor. What they were able to do is use the system to first get the consistency, right, of their slump, and in this case, that means a lot of other things, right? It's not only just water, but also, as you saw before, the time it takes to get to site and when they're pouring. They were able to really bring that consistency down, and then the middle graph here just shows the standard deviation in water at discharge for a variety of customers with a very similar mix design. All right. So it's a wide variety, again, and basically how consistent they are. And you can see this, the contractor here, this is where they lied, the very, very smallest part right here. So they are controlling their water as best as possible. So once they did this, they started to look at their strengths, and for some strange reason, the strengths looked really good, right? Not only that, but when you apply this to how you're designing your mixes with your over-design, they realized that their mixes were way over-designed. You got your consistency, your standard deviation went down, and then they could basically look at that and start to take out their cement. So they did this with two different mixes. You have a channel mix and a barrier mix. These are the original, and so basically this is a little histogram of the strength, actual strength test that they have for the original here, and then they took out 50 pounds of cement per cubic yard. And then these are the resulting strength distributions. What I just want to point out here is the solid line here is the required strength. So you're still above your required strength, and your design strength is this dotted line. So they were able to, again, control it with their consistency, take out the cement, meet their specs. But on the other hand, that's not everything's over. They're always monitoring the data to make sure that they're in that sweet zone. All right. So if they come out of that sweet zone, they know they need to fix something, and then you got to be really careful about low breaks and things like that. All right. So just some future looks, some of the stuff that we've been playing around with. You can do this on a wide scale. All right, so this is just, for example, these are two different specified strengths here. I think it's like a 4,000. So again, this dotted line is the specified strength. The specified strength. So 4,000 to 4,500, and the black line is that ACI required strength. All right. So you can do this, look over your entire catalog of mixes. This brings up a lot of questions, right? I mean, why do you have 20 different 4,000 mixes? Could you get around with maybe 2 or 3? There's absolutely, you need more than one because there are different situations for this to go into. But this allows you to look at this. Not only that, but it allows you to look at some of these way over designed ones, these ones here, for example. Is there something with, are they using a special aggregate? I mean, why is the cement efficiency so high for those? And so you can really start to look through your catalog and optimize your decisions that way. So just want to wrap up with this future outlook. There's a lot of opportunity with visibility and control. So, just our base numbers, we're looking at, about 15% of your total volume can take out at least 25 pounds of cement. This is not, waiting for certain things. This is you have the data and you can do this today. So when we talk about immediate impacts to the environment, CO2, this is a really good way to start down that path. And then not only that, but things like durability have really positive impact once you start doing this control. So with that, I'll have any questions.